Okay, you're on the air. So we're going to call this isotopes and average atomic mass. Isotopes and average atomic mass. So we already introduced the concept of isotope last time. And an isotope is, we have isotopes when we have the same element, but the atoms have different mass. So same element, different mass. And this thing's not cooperating. So we have things like, let's look at carbon, for example. There's carbon-12, carbon-13, carbon-14, all right? And I might have already drawn this, but I'll do it again, and we can write protons and neutrons. All three of these have 6 protons, but they have different numbers of neutrons, all right? And this number right here, where it says C dash something, that's called the mass number. And that is equal to the number of protons plus the number of neutrons. Now, sometimes you'll see it written like this. All right? So there's other ways of writing that, and as we get into nuclear chemistry, we're going to start using this method more. But you'll see both forms of notation, both ways of showing different isotopes. Iso means same, right? So different isotopes. Now, our system of relative mass is, so our current system of relative mass atomic mass is based on carbon-12, which is a particular isotope of carbon that's right here, carbon-12, being exactly 12 atomic mass units. So that is, by definition, AMU. Okay? By definition. Current system of relative atomic mass is based on carbon-12 being exactly 12. So if we were to write the mass of these things here, we would write exactly 12 for carbon-12. And if you look in your book, we're in chapter 5 now, there's a table with some examples of atomic masses in it, some masses of some isotopes. It's on page 119. There's a table. And if I look up carbon, I see that carbon-13 is 13.003. So notice the difference here. When I wrote the mass of carbon-12, I wrote exactly 12. When I wrote the mass of carbon-13, I gave you 5 significant digits. Right? This carbon-13 is relative to C12 being exactly 12. So just like in John Dalton's system, everything was relative to hydrogen being 1. Right? In Dalton's system, everything was relative to hydrogen being 1. Now, it turns out the masses aren't going to be so different doing it this way, because the carbon-12 atom has 6 protons and 6 neutrons, and so it's about 12 times as massive as a hydrogen atom, which only has 1 proton. Now, I've got here a table of all the stable isotopes of all the elements. So let's see, let me zoom in a bit here. So what they've done here is they've measured these. So you can see here, this is the mass of hydrogen 1. That's just a proton. Hydrogen 1, see this is the mass number up in the upper left. Hydrogen 1 is just a proton, no neutrons. Here's the mass. And that little U means atomic mass units. Look at that. There are 10 sig figs in that number. They use a mass spectrometer to get this thing. The number in the parentheses is the uncertainty in the last digit. So this number is plus or minus 0.00000001. That's the uncertainty in that number. So these are some pretty darn precise numbers here. You can see hydrogen 2 is approximately 2 AMU. Not exactly. This has a proton and a neutron. Hydrogen 3, approximately 3. A proton and 2 neutrons. And then you can see there's 2 isotopes of helium and so on. Some elements have only one isotope, like fluorine. There's only fluorine 19. Others have lots of them. You can see nickel has 5 different isotopes. Now, there are not an unlimited number of isotopes like you might think. You might think, oh, if I could just add any number of neutrons, I could make all sorts of different isotopes. But it's not true because, as we'll see next week, changing the number of isotopes changes the stability of the nucleus. So if you don't have the right ratio of protons to neutrons, the nucleus will become radioactive. And these are stable isotopes. So it can become totally unstable and just break down immediately if you don't have the right balance of protons and neutrons. That's why there's only certain isotopes allowed. We'll get into that more next week. Now, I want to give you did I give you a periodic table yet? No. Like this? Okay. Pass this around for me. And when you look at a periodic table, of course, we're going to be spending a lot of time looking at periodic tables, but you'll see something like this for carbon, for example. On this one, it has a big 6 above the carbon, and of course, that's the atomic number, and that is the number of protons. That's the number of protons. But then underneath that, it has a number that's not a whole number. So for every element, there's going to be one whole number, and then there's going to be something that's not a whole number. Something like that. Now, here's my question for you. When you look at that box and you see that number there, 12.0107, and then I tell you that this is the mass. That's a mass. It's a relative mass. You have to wonder. Yes, go ahead.
You just stated the relative mass of. Oh, never mind.
Go ahead.
Right,
Finish what you're going to say.
12 was exactly 12.
Right. So why is this not exactly 12? That was exactly what my question was going to be. I was going to say, why isn't this number under here exactly 12? Why is it 12.0107?
Electrons.
Okay, it's all kinds of carbon, it's different isotopes, right? So the reason it's not exactly 12, so we could say, why is it not exactly 12? And the reason is, so that's the question, the answer is not all carbon is carbon 12, right? Now it turns out you can tell that most of it is if you look at that number, because this is actually the average atomic mass. All right, that's actually the average for all the isotopes. So you can tell by looking at that the vast majority of all the carbon out there in the world is carbon 12, because it's pretty close to 12. Now, for some of those masses, you can tell that there's a pretty good mix of different isotopes, and we'll see. So let's look at the actual abundances. See, if you look at this chart, it's got two things on it. It has the mass, and then it has something called abundance. Abundance means what percentage of the element is made of that isotope. So scientists go out into the world and they collect samples of carbon in different places, maybe some coal, maybe some graphite like you're writing with in your pencil, maybe the ashes of some dead king or something like that. And they take different samples of carbon and then they put them through a mass spectrometer, measure the masses of the carbon atoms, and figure out what percentage are each isotope. And if we look at carbon, we see 98.90 plus or minus 0.03 is carbon-12, 98.90%.
What is the star?
The star, let's look at what that means. A star in the abundance column indicates a radioactive nuclide not present in nature or an element whose isotopic composition varies so widely that a meaningful natural abundance cannot be defined. So either they can't get a good reading on it, maybe it's too small of a percentage, or it's too unstable. So if we look at carbon again, we see that carbon-14, which is radioactive, has a little star by it. And carbon-13 is about 1.1% of all the carbon. And you can see there's abundances for all these. One of the things you notice, first of all, is there's a lot fewer sig figs for the abundances. A lot more uncertainty. Yes?
If like radioactive isotopes like carbon-14 are so small that you can't find a mass for them, then how do they do carbon-8?
You can find the mass. Here's the mass. They can't find a percentage. Now, let's talk about that, though. Why would you be able to get 10 sig figs on the mass, but only 5 or 3 or 2 on the abundance? What is the abundance is like what proportion of the carbon is, that isotope? Why would you be able to get so precise? For one thing, the mass is determined in an instrument where they shoot an ion of the atom through a magnetic field, and they're able to measure the deflection, basically, change the deflection of it, get the mass very precisely. This is extremely precise numbers here. Yeah.
Because the abundance is always changing.
Okay, so it could be different. So if I took a carbon sample from the ashes of some dead king, and then I took a carbon sample from coal in Pennsylvania, and then I took a carbon sample from graphite mined in Africa, right? And then I took a sample of CO2 from the atmosphere and took that carbon. Am I going to get exactly the same percentages of the different isotopes? Apparently not. Okay? So they can apparently vary. And you'll see some of them are much more precise than others. Some are really not precise at all. Like here we've got some pretty good numbers. It's got 6 sig figs here for potassium. So some of them are apparently more consistent than others in terms of the ratios. Now I don't know why carbon-14 shows up like this. Apparently maybe it's too small of a percentage to get a reliable, maybe it's overwhelmed by the uncertainty at that point. Yes?
What is the B? It has 100% abundance.
Yeah, beryllium. So there's only one isotope, only one stable isotope of beryllium.
It's the same thing with like the SC.
Yep, and the fluorine and sodium actually. Sodium only has one stable isotope. So it gets pretty, I don't know why in some cases only one isotope is stable, and in other cases there's more possibilities.
How is it considered an isotope if it's just one kind? Like if there's only one.
Yeah, you're right. I guess we still would say like there's only one stable isotope, even though
It's like
there's only one atom, but you still use the word isotope in that case, I guess.
So like
Yeah.
carbon is not an atom itself, it's a classification of atoms? Like a
Yes.
classification of isotopes?
Yeah, I guess you could say that. Yeah. An isotope is just a particular combination of neutrons and protons, I guess you could say. I guess you could say it like that. Because you're right. The way I defined it, it seems like you wouldn't even call this an isotope
Right.
because there's only one option. Now, how do they get this average? So here's our average, right? We said that's the average mass of carbon. So how do we calculate the average? How do we calculate the average mass? Well, first of all, you might be tempted to take the two masses. What are they? It's 12 exactly 12. And then we can look on here to get the other one, 13.003354,838. Okay? You might be tempted to do this, but you wouldn't want to do that. Why not? You can tell me why.
Because
Yes.
it's more C12 atoms than there are C13.
Right, this is 98% of the carbon. So we don't want to do just a straight average, just like this. Just take the 2 or the 3 or the 5 or however many masses and just divide them. You don't want to do this. Okay? Don't do that. Yes, James.
Did you do 12 times 98 plus 13 point whatever? 12
All right.
times 2.
Where's my, what was it? 98.90 plus, what'd you say? 13,
13.003354,838
yep, times
2 or times 1.1.
1.1, right? Yep. All right, so now, think for a second before I move further here, because we're not done with this calculation. What am I really doing? What I'm doing is I'm saying there's this many atoms out of 100. In other words, for every 100 atoms, 98.9 have a mass of 12. For every 100 atoms, 1.1 have a mass of 13, right? So I need to divide this whole thing by 100.
John's doing 200.
No, because that would be sort of.
Well, no, look what's happening. 98 of them are 12, have a mass of 12, and one of them is a mass of 13. That's, or 98.9 and 1.1, that adds up to 100.
You're doing the distribution in the numerator.
Right. So I'm just going to divide by 100. So let's see what I get if I do this calculation. Let's open up the great calculator. You're not always going to have to use so many digits as I have up here for the mass. 98.90.
Do you have an actual calculator over there with you, or is that on the computer?
This is on the computer. 13.003354,838 times 1.1 divided by 100. It's off a little bit from what I wrote on the board. Let me see why here. I don't know. Sometimes they update these numbers, and depending on where they got the values for the periodic table you have in front of you, they could be slightly different. 12.011 is a common value you'll see for carbon.
Could you first multiply, like, instead of multiplying 12 by 98.90, could you multiply like 0.98?
Yes. In fact, I would suggest you do it this way. The second way here is that you put the percentages into decimal form. Then you don't have to divide by 100. And the reason I say that is sometimes you'll be solving for an unknown in the equation, like an unknown mass or an unknown abundance, and it'll be easier for you if you do it this way. So this is just converting the percentages, the abundances, to decimal form first. Okay? Yeah. Go ahead. Now, sig figs work kind of weird on these, and we always have to be careful of using the sig fig rules when we're calculating averages. Did I mention that before? Calculating averages with the sig fig rules can get you all messed up. And if you do it like this, you're guaranteed to come out with fewer sig figs than you have on that table in front of you. And so I'm not really sure how to get around that. I think what it comes down to is I'm not going to be paying too much attention to sig figs on these problems because I'm not sure how to deal with it. What's going to happen is the only way to really do it would be to actually use the uncertainties that are given to you on this table and then turn them into percentages, add them, and carry them through into your answer. But since I'm not going to require you to do that, and that would work, that would give you the proper number of sig figs. But I don't want to. I'm not going to give you this kind of information on a test. All right. The sig fig rules will not work. They'll give you a distorted picture of the significant digits. All right. How come? That's a good question. So let's do a little aside here. Let's say we had some numbers, and we're going to calculate the average. Let's do this 1 point. And we're going to divide by 4, right? And we want to know how many sig figs we're going to have. So I take 1.2 plus 2.3 plus 1.5 plus 1.7. That gives me 6.7, right? Which would be, well, here, let me make this a little bit more interesting. And then I'm adding some more, sorry, 1.8. I want to make a point here, so. This total is 8.0? All right.
It's just 6.7.
I got 10.8.
No, because she had. Oh, yeah.
All right, 10.8 over 4. Now here's the thing. Not over 4, sorry. Over 6. How many sig figs would you have if you use the sig fig rules in your answer? 3, because you go by decimal places when you're adding, right? So we'd have 3. So here's what we get. 10.8 divided by 6, 1.8. But look at the discrepancy here. If you used your plus or minus notation, let's see what we would get. Well, maybe it might work out in this case, but in some cases it won't. Let's take 1.8. That the deviation there is 0. Here it's 0.6. Here it's 0.5. Here it's 3. Here I didn't make a very good example because. So our maximum deviation in this case is 0.6. I guess it worked out in this case. But you could. What's that?
Could you explain why it's 3 sig figs again?
Oh wait. See, look. Yeah, that's where I messed up. First of all, with 3 sig figs, this would be 1.80, all right? But that can't be right because I just calculated my deviation. I'm coming out with 0.6. I really should be writing it like this, with 2 sig figs. So what happened? Why is it 3? Because when I add these up, I'm adding numbers. And the significant digit rule is you go by the lowest number of decimal places when you're adding numbers. Which means this sum, 10.8, would be allowed 1 decimal place, just like I've written it. But that's 1, 2, 3 sig figs. Now when I do the division at the end, I carry through 3 sig figs because I'm using the division rule.
So because
Okay.
we're adding them, it's not that we have the lowest number of sig numbers that we're adding
It's
to
decimal places.
decimal places.
Right. Now, so that creates a problem because it gives me the impression I have 3 sig figs when clearly I don't, if I just look at the data. Now, we had this big discussion, me, Mr. Turshot, and Dr. Bent, and basically what it comes down to is the sig fig rules are just a cheap substitute for plus or minus notation. All right? And if you can, you use this. All right? And if you're calculating an average, then you can always use this. Because you have a bunch of data that you're working with. You follow me? So, now exactly why it causes a problem, I'm not really sure. It's just basically that the sig fig rules don't work for everything because they're just a cheap trick. Not worth the paper they're written on.
Why did we learn them?
Well, I shouldn't say that. That's a little extreme. So anyway, because I'm not going to make you deal with the uncertainty on these, I'm gonna say just put some extra digits on there.
So if we
All right.
didn't follow the thing you just did, that's okay.
Right. Well, let's see. I mean, how could you do it that way? Could we use this data to get a plus or minus, a maximum deviation? I guess you could actually. You guys didn't want to hear that, could you? Let me think about that more and I'll get back to you. All right? For now, just keep some extra digits. Let's try another one here before we're going to do a little activity here in the next period. Let's take something interesting. How about magnesium? Magnesium is an interesting one because it has pretty even distribution of its isotopes. I'm going to take the magnesium data over here. And we're going to calculate an average again, just so that you can see another example of it. So here's my magnesium data. These are my masses. These are my percent abundances. So the average mass is going to be 23.9850419 times 0.7899. I'm using the decimal form of that. So I'm dividing by 100. 24.985837 times 0.1000. And then the last one is 25.982593 times 0.1101. See how that works? Is anybody stuck on this step here where I just converted that to decimal form? I'm just dividing everything by all the percentages by 100.
We're still on, like, no.
Yeah. So you don't want to ask a question because you're being recorded? You can ask a question. Nobody knows who you are. I won't say your name. Unidentified student, do you have a question?
Peter does.
Okay, let's do this one.
Wait, I have a question actually.
Yep.
Why don't you use the uncertainty as like plus or minus
2.002.
No, like,
Or you could do that, yeah. So you could, in this case, you actually do have the uncertainties. But here's what you'd have to do. You're adding them, so you would add them in the first step. No, first you're multiplying them, so you'd have to convert them to percentages.
they're all the same uncertainty.
Then you'd have to add them. And you'd get a different one for each pair, each mass abundance pair. And then you'd have to add them all again at the end because you're adding those three pairs to each other. You follow me? So we probably don't want to do that. So let's take 23.985041 times point. Oh, I forgot the 9 at the end. Okay, 9 times 0.7899 plus 24.985837 times 0.1 plus 25.982593 times 0.1101. 24.305. Is that right? What's your periodic table say for magnesium? Let's see, did I get a 2 after that? No, I didn't. So we're off a little bit again. Depending on what they use to make this table.
It's a 0.
You're right.
Yeah, you're right.
Is it?
3050.
305.
Nailed it, man.
It's 24.3050.
Yep. Okay, but this one would actually round up to 5.1 at the end. Okay, so there you go. And if you want, you can put an AMU on the end of this, atomic mass units. Of course, they're just relative units. They're relative to carbon being exactly 12 AMU. See how that works?
Yeah.
Yes, no? I'm going to give you some practice in your book to work on this tonight. This is, by the way, this is called a weighted average. And this is how This is actually how your grade is calculated in many classes. Any class that uses category weights, like with a percent, like your tests are worth 40%, your lab's worth 40%, your homework's worth 20%, whatever, they are using a weighted average. And the grade book on PowerSchool is using a weighted average. We're just giving different masses different weights based on their abundance. Now, fortunately, these things, these abundances are consistent enough that we can safely use the averages printed on that periodic table and come out with good results when we're doing chemistry. Okay? And that's that.